All right, section 10-5, calculating the rotational inertia. So we've talked about it. This is where we're going to focus on not just a series of particles that are rotating around, but actual full objects or bodies. So if we have a continuous body, then we'd actually need to do an integral in order to carry this out. So we could integrate over r squared over dm over all the little mass elements that make up our object, like a marker, right? Integrate each of the pieces there and how far away it is. So in principle, we could always use this equation, but there's a common set of shapes for which values have already been calculated for various axes, and that's our table 10-2. So this is table 10-2. It's a great reference. It's something that's given to you on the exam. So it's not something you have to have memorized, but you do need to know how to use it. So we look at each of the shapes here, such as a hoop, and it tells you about the central axis. That's how the hoop is rotating, that it is rotating around that long vertical line. You could also then have a ring, right? So something that's not super thin, or solid cylinder or disc about the central axis. Notice there's also a solid cylinder disc about the central diameter. So that's saying in the first one up here in C, it's rotating about the central axis, so it's just going side to side. But in D here, it's about the central diameter, so it's rotating instead end over end, is what that's trying to depict. You can instead have a thin rod or a solid sphere, thin spherical shell. Here's a hoop again, but now it's about any diameter. So this is like with if you spun a quarter and assumed it was a hoop, or a slab, which this is the rotational inertia equation we saw in lab last week in the bullet block mystery. So these are all interesting and really useful to be able to use them. We noticed that they all involve the mass m, and then usually a radius and or a length L. Now, in addition to that table is all the rotational inertias about the center of mass. They're just inherently that way. Once we know that, once we have that from table 10-2, we can find the moment of inertia for a parallel axis, for another axis that's nearby with our parallel axis theorem. So our parallel axis theorem says that our rotational inertia about any axis is equal to the rotational inertia about the center of mass plus mh squared, where h is the distance offset from the center of mass, right? So here, the pink one is the center of mass. That's something where we know the rotational inertia, probably from looking up table 10-2. And then if we want to look at the rotational inertia about point P instead, then we know that that's a distance h away. So we add that h squared plus the total mass. Couple key notes. One, the axes must be parallel. So we can't just have axes pointed any which way. They have to be pointed parallel to each other. And the first one must go through the center of mass icon. So this doesn't relate the moment of inertia for two arbitrary axes of rotation. Once again, they need to be parallel. Right, so let's look at an example with this, and this is from a different textbook, Young and Friedman's University Physics. It says to find the moment of inertia of a thin uniform disk of mass m and radius r about an axis perpendicular to its plane at the edge. So one of our challenges here is first to picture what's going on. It says it's a thin uniform disk, and the key here is an axis perpendicular to its plane. When it's talking about plane there, it's talking about that's the plane is the flat part of the disk, right? So if I try to sketch this out, I can make a disk there, right? And it has a center, some radius r, and we want to find it at an axis perpendicular to its plane and at the edge. So I would draw this over here. That would be my axis. I'll stop the share for a moment so we can see this a little better. So we have our disk, our axis, and we want to find the rotational inertia about this new axis. Well, what do we do here? this is a case where the axis that we want to find is definitely not the center of mass. But what we can do is, if we know the rotational inertia about the center of mass, which is at the center because it's a nice symmetric object, then we can use our parallel axis theorem to get it about this new rotation axis. So center of mass would be in the middle here. So I'll label that icon. And if we look at the table, 10-2, I encourage you to take a look. We want a solid cylinder or disk. So I'm going to use the disk one, and I want to use the one that's going through the central axis. So that one says that my rotational inertia about the center of mass is equal to 1/2 mr squared. All right, so we have that as a resource. If we want to use the parallel axis theorem, let me write that out. We know that our rotational inertia will be equal to icom plus the total mass times h squared. All right. So icom we have right here, 1/2 mr squared. And then we have m, and the problem told us it's in terms of capital M and R. So that means we know that our final answer is going to be in terms of probably capital M and capital R. So that's okay. So I can plug that in with this icon. That would be 1/2. I'm going to make it a big M because it's the total mass times R squared. Cool. Plus big M, that's still okay. And then what we have left there is the H. And H, remember, is the distance that we are offset from the center of mass to this new axis. So that distance is our distance h. And in this case, conveniently, notice that's just the radius of the shape. So I can plug in an r, capital R, and squared. So then we just have 1/2 mr squared plus mr squared. And so we get that our rotational inertia is 3/2 mr squared. Right. So going back to this now, we see the end result of the full solution here, and that is all well and good. Right, here's another example that comes from our book. It says to calculate the moment of inertia for figure case B, which shows a rigid body consisting of two particles of mass m connected by a rod of length L and negligible mass. The negligible mass there tells us that we don't actually care about the rotational inertia that the rod contributes, that we can say it doesn't matter, and we can just focus in on these particles. And it tells us too, for figure 10-13A, the rotational inertia is 1/2 ml squared. Well, it turns out there's two different ways we can approach solving this, and they're both valid. So since we know the rotational inertia for part A, which is about the center of mass, then we're able to find it for part B because we notice the rotation axis has just shifted from the center of mass to a new axis. So hey, we can apply our parallel axis theorem here. The other approach we could take in case B that's equally valid is we could say that these are just two masses that are rotating. There isn't a set rigid body here. And so we can just look at how much mass each of these contributes and how far it is from the center. So that's using our I is equal to the summation of mr squared. So let's take a look at those two solutions. So if we use the parallel axis theorem, we're using icom plus mh squared, and icom, which was given to us, is 1/2 ml squared. And then the total mass here, we have to include both of them, is 2 times little m. So we plug in the 2m there for the total mass, and the amount that we are shifting is half the length of the rod. So I plug in a 1/2 L and I square that, so it becomes L squared over 4, but times 2m, so it's 1/2 ml squared plus 1/2 ml squared, that just comes out to ml squared. The other approach we could take because these are just particles, we can sum them up by adding up each of the rotational inertias due to the particles. So this is following the equation, summing up m times r squared. So the first mass is at a distance of 0 from the axis of rotation. So it contributes no rotational inertia, m times 0 squared. The second mass is at that full length L, so it's just m times L squared. So the total rotational inertia just comes from that one particle that's out there hanging out. So that's a useful way to think about this. Right, finally there's a checkpoint here. Figure shows a book-like object, one side is longer than the other, and 4 choices of rotation axes, all perpendicular to the face of the object. Rank the choices according to the rotational inertia of the object about the axis greatest first. So I want you to take a moment to think about this. Go ahead and hit pause, and then we'll check back in a moment. Okay, hopefully you hit pause and thought it through. So now we look, and the greatest rotational inertia is 1, followed by 2, and then 4, and then 3. So what is it saying? Well, we know the rotational inertia about the center of mass is something fixed. Anytime you shift off of the center of mass, it becomes harder to rotate because you have more of the object that's further from the axis of rotation. We could show it with my calculator again, right? So 1 is the furthest away from the center of mass, and so it's going to be the largest amount of rotational inertia. 2 is at least closer, but it's on that diagonal. 4 is then the closest to the center of mass, versus 3 is right on the center of mass. So 3 has the least amount of rotational inertia, even though it definitely still has some there. All right, we'll wrap up there. That is section 10-5, ways to calculate the rotational inertia. See you soon.